let's finish up or not finish up actually. This is going to be a three lecture set of slides. We're going to talk about classes some more though. We talked about structs. Now we are moving on. We're doing class stuff. It was beautiful. We gave operations to our point type. It was awesome. And yeah, it kind of looked like this, the way that we implemented class point, public colon. What did that mean? We'll figure it out. Give the kind of data that lives inside of this type, as well as the operations that can be performed on it. And it's always in terms of itself, like, hey, point, negate yourself. It's not a function, it's a method. Remember, member function, right? So I get to tell you now that I was being lazy last time, just to make it easy for you to understand. I implemented all the class in one big chunk all together, but that's not usually how you're supposed to do it. Right? I implemented all those methods inside the point class, when in reality we should have been splitting it up. We should have been like making a little point library with a header file that declares all the stuff and a CPP file that implements all the things. So let me copy in the stuff from before. No, sorry, lecture 14. I guess we called it classes.cpp, and I need to copy it into a new file. And how about I call it point.cpp? Right. So I'm going to add more to it. So everything was done in the class itself. Like I gave the bodies here, but that's kind of lazy. We don't want to do it that way. Right. So wouldn't it be nice if we split it up? We made a header file and a CPP file. We could have even like split it up in the same file. I'll do that first maybe. But we want to move, we want to just declare. We want to declare everything that exists in this class in this part. This should just be the declaration. And then we'll implement the things. We'll implement the methods outside. All right, so that's going to be our goal. So I'm going to move scale and add and negate outside of the point class. Remember those. All right, I have to shift them all over it like that. And I do need to declare that they exist in here, though. So let's steal that guy, that guy, that guy. So these are just the declaration pieces now. Oops. There's all that. Get over there. So now I'm declaring that they exist and I'm trying to implement them outside. All right. But right now this won't compile because what does this look like? It looks like a function, right? And C++ can't tell. Like, is this a method? I have no clue. You're talking about X. X doesn't exist. Well, you're crazy, dude. So we have to tell it, no. This is linked. This is linked to the point class. This is the negate method. It is not the negate function that lives outside of a things. All right. So the way that we do that is we qualify its name. All right. Once we put stuff outside the class, we have to tell it C++ like, no, this isn't a function. It's a method. It belongs to this class. Its full name involves the name of the class itself. So it's going to be point : negate. So the full name of this guy, this is not just void negate the function. It's points negate function, negate member function, negate method. So name of the class : name of the method. That is informing C++. Now this is a method. Be happy about it. And remember your semicolons. So that one's happy now. It's points add method, point : add. It's point scale method. It's not just a scale function. Now x and y, it understands that they exist. All right, so that's the new thing. And so kind of read that : as apostrophe s, just like we were doing before. Let me fix these. So just read that : as apostrophe s, just like we were doing standard : I don't know, string or cout. It's the standard libraries cout thing. Okay, so it's the point class's negate method. That's how you just qualify things. It's points at. Right, so that's what you do, and it's going to work now. Now that everything's outside, it's happy. Correctly qualified. Everything is as it was before. Question? It was always like that. When we did the very start of class, it was standard : cout. That's just what you do. There was never just one. Okay. Yeah. Oh, did I mess something up? Oh, 2 semicolons. Sorry, yeah, that I did mess up. That's why, actually. Yeah, it messed up my braces, and then I had to add a new brace and a semicolon, and I think it left the old one there, but I got rid of the brace. So sorry about that. Yeah, that was, I mean, it's not an error. It will still work, but it was wrong. I think you had your hand up first. Yeah. I'm in just the file that we worked on last time. It was classes.cpp from last time, and I just renamed it. I'm calling it point.cpp today. Yeah. Exactly, because otherwise this looks like a function and it doesn't understand. Well, there's a few things. So first of all, there's a header file. We're about to separate this into a library, make a header file, make an implementation file. Honestly, I can't give you a good answer in CSCI 40. The reason why you shouldn't do it that way is because it's going to be baked in at that point. It's what's the word? If you do it inside the class, the method is inlined, and that is a word I'm not going to teach you in this class. And you usually don't want that to happen. It's going to make your code blow up whenever you use the methods. So just take my word for it for now. It'll be able to be compiled separately this way. That's going to be helpful. Another question? Yeah. So it's, when you implement a method inside a class, it inlines that method everywhere you use it, which copies code, if you want to look that up. Inline. Yep, that's what I'm about to do. Excuse me. So, yeah, let's split this guy up. Let's do it like this. So I'm going to make a point.h file that holds the declaration of the point class. Point.h, and that's where I'll shove this. Boop. And then I need my header file guards, of course. So let's put that in the middle of these to prevent against infinite inclusion. What else? So that needs to go there. This is the declaration. This is just the declaration now. Declaration of the point class. Oh, and I'm so sorry, guys. My apartment complex is calling me right now. They said that my water heater is leaking in a text message, and now they're forcing me to talk to them. So here, you guys can hear my struggles. Hello? Hi there. Okay, that's not a problem. Just try to not let my cat out, please. Thank you. Bye-bye. One of the joys of renting. All right. So, where was I? This is the declaration of the point class, and that's that. We have the implementation in this file. There it is. This is the implementation of the point class. I honestly don't need any of these guys here. That can be part of like the main function. And so I'll make a third file that uses the point class. That's where I'm going with this. So this is it's like the implementation of the point class right here. Implementation of the point class. And then I want like a main file. So main.cpp, where I will put all these. All right. And so if I'm going to use this point class, I need to include the header file for it, include point.h, because that's where it's defined. It's happy about it, understands that it exists now. And I think that's most of it. There's one last thing to do. Point.cpp is like, what do you mean? I don't know what point is. And so this is why I told you to get in the habit of including your header file. You need it here now. You always need to include your header file when you're implementing a class separately, because it needs to know that that name of that class exists, and that is given in point.h. That's where that type gets created. All right. So there is that. It seems to be happy, and so I have 3 files right now. I've got let's see. I got the main file that uses my point class. I've got the declaration of the point class, just the declaration, no implementations of those methods. And then point.cpp holds the implementations of all of the methods that we promised to make in the header file. All right, so they're all working together. Does that make sense, that way that we split it up? It's very similar to writing a library for functions. It's just like you're declaring an entire class somewhere. right? And then to compile it, we're going to give just the implementation files. We're going to say G++ take all of the CPP files, main.cpp and point.cpp, and we'll call this this final file, I don't know, let's call it point this time. So there it is, point, and everything still works. Okay, does that make enough sense still? All right, so let's see here. What else do I want to do? That's enough for that slide, I think. So yeah. I hope I have a water heater when I come home. That's going to be an interesting issue. All right, so let me tell you about that public thing. All right, public versus private. I said public here. What in the world does that even mean? All right, now is time. Ooh, there. So public, I think I said that once upon a time. It just means that everything that you mark as public is accessible to the user. Everybody gets to see it, even the people outside of your class. All right. So by using public, we gave like complete access to everyone and everything. Anything after public is visible to the user, we say. All right. So everything underneath this public colon is accessible to the user of our class. All right. As the implementers, like when we're making the body of negate and add and scale it, we're allowed to do whatever we want. Right. We have total control. We're the ones making it. But the people using our class, like in main, right? They're just using our methods and member variables. That's not part of the class implementation anymore. That's outsiders, okay? So sometimes you want to section off some pieces of your code, all right? So everything after public is visible to the user, and so they're allowed to do stuff like this. Int main point p.x equals 42 or whatever, p.negate, among other things, right? So sometimes we don't want to give the users control of stuff that's just for us, the implementers. So like we don't want them to mess with stuff. And so there's a private, right? Public implies the existence of private, and that's going to section off parts of our code that we don't let the user use, all right? So let's see here. Things that should be private should include your member variables. Your member variables should never, ever be public and accessible to the user. And let me try to give you a good reason why. Like, we don't want this line to ever be able to compile. All right, and I'll give you a good reason why. We never want the user to be able to directly set our member variables because we lose control over them at that moment. All right. What if we made a point class, right? Pretend we made a point class where we only want to be able to represent points that are in the first quadrant, right? Only positive x and positive y. If, right, we only want them to be over here. If I give the user control over the x and y member variables, they can totally be like, bam, negative. And I lose that idea of them always being over here. Do you see that? I lose that idea, like they're allowed to put it right over there now if they wanted to. And I'd like to disallow that, okay? So just if they can set a variable, they can mess with our invariants, that's the word, right? The things that we expect to see inside of our objects. And so instead of this, like we should disallow this with a private. I'll show that to you in a second. And then give them like a method, like set the x part, hey user. Like give them a method that sets it, and then we just like check in that method with an if statement to make sure they're setting it in a way that we allow. All right. So that's kind of the goal. That's what private will give us, and we'll do that in just a second. We're going to make all of our member variables private. Okay. Let's see, what else do we want to do? And then we should also learn how to test classes, right? Just like we test functions. So let's do that before we do public-private stuff. So, all right, how do we test things? So we have to make a little tiny version of a program, a little mini unit test, right? Mini program to check something. And so it's just like a bunch of things, a bunch of lines where we understand what should happen, right? Because we're going to run the program in our minds and like imagine what should have happened. And then we go and we check with an if statement or a search true, right? To see if that thing that should have happened matched what we actually got, okay? So that's the goal. We'll use a search true, like an if statement, to compare what we got back with what we expected. And so let's make some tests for negate and scale on our point class. It'll be very similar, all right? So like, this is always the key, got versus expected. And so here's like an example of a test for negate. It's a little bit different than function testing because we got to like make a thing of that type now, right? Point p P dot x equals 42, P dot y equals 43, and then let's say we call P dot negate right there. Bam, all right, P. What should have happened? So x and y should have got set to 42 and 43, of course, and then negating it should make it negative 42, negative 43, okay? So that's what we can check. We can assert that, all right, if you look at P dot x now, it's negative 42. If you look at P dot y now, it's negative 43. All right, so let's do that. Let's do that in the main file. Do I want to get rid of, yeah, let's get rid of all this code, and we'll make tests instead. Whee! So let's make a test for negate. And so that'll just be a void function that does the test inside of it. Usually that's what you do, all right? And I guess I need assert true as well. Where did I have that? That's the easiest way to search for that. Something like that. Oh no, I did it backwards. Okay, lecture 11, testing.cpp. All right, let's do it down here. That's a nice assert true for me. Copy, paste. There we go. All right, so now I have assert true to use. And let's do exactly that. Let's be like, okay, point P. P dot x equals 42. P dot y equals 43. P dot negate. All right, we expect to see now x being negative 42, y being negative 43. So assert true. I assert that this must be true right now. P dot x should be 42 right now, and P dot y, sorry, negative 42. And P dot y should be negative 43. All right, that's the goal. Does that make sense? That'll be our test. Now we're calling it, and we're making sure that it did that. All right, so let's do that same idea for scale. Let's make another point and call scale on it and make sure that we're getting back what we expect to see. Okay, let's call the point Q this time. Why not? So Q dot x, Q dot y. Let's set them to something fancy like 2.5 and 3.5. All right, and then let's scale Q by a factor of 2. And it really is a double factor, right? 2.0, like all these things are doubles. And so what should we see for Q's x and Q's y? This is our scale test, right? They better be, what, 5 and 7? Remember that you should never be doing this, right? You should never be checking doubles for exact equality. Again, I know that it's going to work this one time, but you cannot bank on that, okay? Once you get a computer science degree, you're allowed to do this. Until then, you must do the absolute value and the subtraction, okay? But it will work this one time. But you should never do as I say, not as I do right now, all right? So let's recompile. Oh, I need to run this test too. Let's run it in main down here, test scale. ./point. And cool, they both passed. So we built these objects and we made sure that what they held inside of them was right after we ran one of our methods. Okay, so that's a good test. A couple good tests, I think. Any questions about those? Yes. You'll want to go back to my slides about doubles, because when you check for double equality, you just want to make sure, like, if you expected it to be 5, it should have been like Q dot x minus 5.0. The absolute value of that is really, really small. Remember that kind of thing? That's what you got to check for double equality, because it'll never be exactly equal. It'll just be very close. That's what I should have done, but it would have taken too much thought. Yeah, it's beside the point right now. All right, so yeah, very nice. Let's do the private thing now. This is another key thing. Like, we love classes because they let us package data and operations. And another nice thing that they give us is the ability to section off pieces of our class implementation from the user. It's just for us, the implementers. We can hide stuff from the user. That's very powerful, okay? So, yeah, let's talk about that. So, there's two ideas of classes that we understand right now. There's encapsulation. That's the idea of packaging data plus operations. That's the fancy object-oriented term for that. It's like bundling data and the methods that operate on the data. So, like, every point, we did that, right? Every point, that's just our class declaration. Every point we've said gets these things. They get an X, they get a y, and you kind of think of the methods as living in every point object. Like that point knows how to scale itself, that point knows how to negate itself, every point knows how to add itself to some other point. Like, in addition to the x and y coordinates, they hold their operations, essentially. You can think of it that way. So that's encapsulation. And then the other side, the public versus private thing, is called information hiding. That's our ability to give the user just enough information to use that class that we want them to use, okay? We're going to show them only the public things, only the things we list under the public section. We'll also have a separate private section just for us, all right? And the whole point of having public versus private, there's a couple reasons. One, you want to give the user as few things to use as possible because that gives them fewer opportunities to mess up, one. And then also, if you just give your user public things only, you can go off and they don't know about the member variables or what's involved there. Like, you can go make your class much better. You can make it twice as fast or something, mess with your member variables, and the user will be none the wiser. They'll thank you, right? Because they're not trying to use those things. They're only using the public stuff. As long as the public things you give them still work, you can mess with the underlying implementation of everything. And that's a very powerful, nice idea. Okay? So, yeah, let's do, let's see. I'm going to eventually put private in there. I think I have 2 more slides before we get there. Right? So we're going to do information hiding in addition to encapsulation in just a second. But I do want to say, right, strings and vectors, those are classes. We've realized that by now, yeah? S.at. This is a method, right? It's a method on a string object. Ooh, we know these things now. That's exciting, right? So that's a method call. It's like acting on that string. Go to the index 2 of that particular string S. Hey, S, go here. It's sending in the message, right? Hey, S, go to index 2, and then it'll do that thing. And same with vectors. Hey, vector, go to index 5. Hey, vector, go and tell me your size. v.size. Those are method calls. Cool. Now you know the difference. Now you understand. All right, so now let's make it fancy. Let's do the public and private, and that's going to give us the ability, or that's going to introduce some errors, and we're going to have to fix those errors. All right, so let's use private so that we can make sure this never happens again. So we had right now we can do this. We can say point p.x equals 42. We do not want that to ever happen now. Let's not let the user access our member variables right now or ever. So I'm going to put them down here. So here's public stuff. I'm going to make a private section at the bottom. Private. All right. And I'm going to move these guys down to here. All right. That's cool. So these are things that cannot be accessed by the user. It will not even compile at that point. All right. So watch. It's not going to compile. Here I am in main, making all these tests and stuff. p.x equals 42. This line won't even compile anymore. Whee! All right. Points x. You can use the colon, see? Points x is private within this context. p.x equals 42. And every other line, too, has an issue now. Declared private here. Declared private here. Cool. So we've just limited our access so that we can do the following. We can now make sure, right, that the user can only ever make points that are here. We have that ability now. We can make sure that they can never put points over here in this quadrant or something if we wanted that ability. We can now have it because the user cannot directly touch those member variables. Was there a question? That's right. Yeah. And so we still want to give the user the ability, 42 is a positive number. We want positive x values, maybe. We need to give the user access, the ability still, through a public method, right, to change the x coordinate in a way that we are okay with. And so what we have to end up doing, once we do this kind of restriction to our member variables, which you should always do, you have to add little public methods to either get them back or change them in ways that you allow, though, right? They're called getters and setters usually. So we'll make a set x method that sets x to 42. And then we can have as much code as we want in here, just checking that thing, right? Checking the argument and making sure, okay, was it positive? Was it okay? Was it something I'm allowing here? And so the second you section off your member variables, you usually want to make 2 methods for each of them. One to get the value so that the user can still access it, and then one to change the value. That's called a mutator or a setter. Right? So a getter or an accessor or a setter or a mutator. All right. So a getter gives back the value of your member variable, it's private now, and a setter sets that value. All right. So now you have finer grained control. All right. So let's do that. Let us implement those things. So in the header file, I need to declare the fact that these exist. So I need some getters and some setters. All right, so I need double get x, double get y, because these are double member variables. So get x should be giving back my x member variable's value. Double get x, double get y, and then for the setters, it'll be set x and set y. Right? Set x, set y. And we need to have the user pass along what they want to set in here. So like double D. All right? So this is now giving the user a window into our member variables. They're only going to be allowed to mess with them in the ways that we allow. You can. It's possible that you don't ever want to let the user change the member variables. Only let them use them and see them. You just don't give them a setter. See how powerful that is? It's very cool. So let's see. Let's implement these. It's going to be a very easy implementation. But where do I want to put them? I'll keep these comments. So here in point.cbp, down here at the bottom, let's implement these guys. All right, so let's just give them bodies right now, and then I'll fix them in a second. All right, if the user says point p.getX, we should just return our x member variable's value. Get y, return our y member variable's value. But I'm getting an error right now. Does anybody know why? Like it doesn't know about x. What did I do wrong? That I did do up there. Do we see it? That's right. So C++ right now, this is just a function. It's just a function because it doesn't know it's part of a class. I have to say, oh no, this is points get x method. And then it's happy. Points get y method. Points set x. Points set y. Cool. So now, what do we want to do in the setters? We just want to set our x member variable to whatever d was, or y member variable to whatever d was. But you could imagine that you could do something like this now. You just be like, all right, if d was less than 0, I'm not allowing this. Like, return. Return and don't let this do anything. Oh, sorry. This should be void. Excuse me. Should have been. Did I do it wrong over here in the header file? I did. I'm sorry. So a setter is just supposed to be void. It's just like you do it and it doesn't return anything. It just does the thing and changes it. Excuse me, I was getting too excited. So yeah, that's something you could do if you wanted to implement those checks. You'd include them right there. But we'll trust the user for now. All right. But those are getters and setters. Does that make enough sense? I'll show you where we need to use them now in the main file. Good. So yeah, we're gonna have to turn all these into things like this. Okay. Is there a question first? Yeah. Well, it's still not compiling because I need to change these. If I didn't have getters or setters and I made my member variables private, I would just have a very useless point class because I wouldn't be allowed to change x or y or ever set them in the beginning. And so, like, points have x's and y's, but they're always going to be garbage at that point. Does that make sense? So I need to have this ability still to set the values and get them back, but in a way that I can check in on the user and make sure that they're doing it right. It's just direct access to the member variables is too much control. It's just for us. Only we should have that control as the implementers. Yeah. So like we don't want this to be a thing, and so let's fix it. We're gonna have to say instead of this, how do I want to do this? Instead of this guy, we're gonna say p.setx to 42. That's the equivalent now. All right. Instead of this guy, we're gonna say p.sety to 43. Okay. That's how we fix that. And then same for these. Like you can't say p.x anymore. You don't have direct access to it. You can say get x. The getter will give it back to you though. p.getY. All right, and that's the way you fix it. And you can imagine, like, this is really, really powerful, right? Maybe you didn't even have an X or Y member variable, but you're letting the user set them this way. Because there's another way, like if we've taken a calculus class, or maybe 2 calculus classes. Have we heard of polar coordinates before? That is another way to store points. Maybe our point class is using r and theta rather than x and y. You can use set x and get x still. You can do that conversion on the fly for the user, even though that's not even a member variable anymore. That's really cool, if you've heard of that. All right, so that's kind of a motivating idea, okay? So here is the same idea, set x to 2.5, set y to 3.5. All right, and scale, and then make sure that when we get the x back, I see 5. Make sure when I get the y back, I see 7. And so that's kind of how you have to change it, all right? So that's the use of them, and I hope that makes a little bit of sense. At least it's access control, right? And so it compiles now, finally, and it's going to run and pass. Okay? Any questions about what needed to change there? It seems a little useless and extra right now, but I promise it's worth it in the long run. All right, so that's getters and setters. There's also this is the third way. There's a third way to use const in C++ that you know about now. You can use const in methods. You can put the word const at the end of a method, and what it will do is mark all your member variables as read-only at that point, every single one of them. So yeah, what do you know about const? You know how to make a constant variable right now, which can't change. You know how to use const parameters to functions and methods. You can like pass along a string as a constant reference, and then like, you get the space savings, but you can't change it, right? You can't touch the S. There is the same thing for when you have a method and you don't want it to be able to modify its private member variables. Or it's just, yeah, honestly. All right, because all of the member variables should have been private. So yeah, if you don't want your method to be allowed to mess with its member variables, just to access them, you can put const at the end of your method, all right? And you might be wondering, like, why would I ever want to do that? Like, my member variable should be mine to set. Well, it just helps you from messing up accidentally, honestly. It's helpful when you're testing things because, like, the second you mark a method as const, and I'll show you that in just a second, then you know, like, all right, I don't have to check and see, like, did the member variables change after this method is over because it was const. It wasn't allowed to change anything, right? So, yeah. What's a good example of a method that should always be const and never be allowed to mess with the member variables, just to always look at them only? Every getter under the sun. So like your getX method, right? It was double getX, semicolon. We can say double getX const now. Const, semicolon. Okay? That's what we're going to do, and that's going to make sure that you can never change X. You can only use X. All right? So that's called a const method. And that is a useful thing. It just keeps you from having to mess up, right? One less thing for you to do wrong, which is always nice, all right? So here's get X and get Y. Those should be marked as const, all right? Marked as const, and then you have to also do that in the implementation, all right? You say const here, right? You say const here. Because if we didn't have this, you could have done something like this. You could have said maybe, I don't know, in get Y, you could have been like, you know, X equals 42. If there was no const there, it would have allowed that, right? Or Y equals 42, doesn't matter, right? And then return Y. Like, that's obviously incorrect, but maybe there's a different kind of method you can think of that, like, you might accidentally do that one day. And just marking it as const keeps you from making this mistake. It's really nice. It won't compile right now because I marked it as const. It's like, ooh, assignment of member point Y in read-only object. It marks your object as read-only for a split second every time you use the method. Okay? That's pretty nice. So this should not be allowed. And that const makes sure it isn't. This should not be allowed. All right? That's pretty cool. So just make sure that you can't do anything silly like that, which is useful. Are there any other methods here that should be marked as constant? Ones that should not be allowed to change our own member variables? Nice. Yeah, I think add. Add's going to be the one, right? I think every other one negates messing with the member variables. It needs to, right? It needs to change x and y. Scale needs to change x and y. But add is just using our x and y. Using our x and y and some other points x and y to make a brand new third point. See that? It's not going to mess with our own member variables. It's messing with somebody else's technically. So this can be marked as const as well. Good. So we can mark our add method as const, and you got to do that in the implementation as well. So it's add const at the end there. It looks a little weird the first time you see it, I know. But that is good. And so that keeps us from messing up and accidentally like changing Rx somehow. Can't do that anymore. So that's really good. It's just a whole class of errors are impossible the second you notice that you can start shoving const at the end of things. So look into that as much as you can as you're implementing stuff. But I think that's what I wanted to say about that. Are there any questions? Yes. It's just the special way that you do it. If this is where you put it, when you want the method itself, every member variable in this object to be marked as const. Because if you say it up here, that's talking about the return type. Now you're returning a const point. That's a completely different const thing. Okay? So that is, yeah. It's just a type difference. Yeah, that's where the return type goes, and so that's not good enough for us. Yeah, that's just why they chose the end. Other question? No, because you're not defining anything. You're just using stuff at that point. Because here I am using stuff. Point p dot set x. Yeah. All right. So with all this, let's see. I guess it's your turn. Here, I have a question for you now. So here is a class definition. Class blah. It's got some stuff, right? It's just very simple. It's meant to like, all right, it has an x member variable. It's allowing you to set the x member variable and get the value back. Sure. So you can make a blah b and do stuff with the b object. So yeah, there are a couple things that are bad practice right now in this class that we talked about today. I can think of two things that are wrong. See if you can find them too. Help the people sit next to you and try to maybe, I don't know. You can write down your answer. Why not? Right? Let's see. Let's go to the written nice page. Please, you can just write in English, like elect a leader of your group. Like, tell me this needs to change and this needs to change. I can see two things, but see if you can find at least one, please. What can we do better? Let's press submit if we're feeling lucky or confident. Let's see what we're thinking. Nice, nice, nice. So, yeah, I think we got the two things. Good job, group 25. A getter should have been const, and every member variable should always be private. That is the point of that. So, yeah, I think we got that. Very good. Awesome. Good job, guys. So, okay. We should have placed const right there. That's important. And then this, we should have said private here. Because right now, without those things, you could have been like blah b, and that makes a b object, and it has an x, as usual, set to garbage. You could have done, like, the whole point of having a setter is saying that set x 42, that'll do that for you, assuming 42 is allowable, right? You have control now. Once you hit the body of a method, you could have an if else. Make sure it's the right thing. It's making sure that you can't do something like this, right? The whole point is access control, make it private so you can do that. Right? Make sure that you cannot just straight away set it to that kind of thing. All right? So I hope that makes sense. Any questions about that? Those are kind of the two main ideas there. All right? And I think there's one last thing that I want to show you. You can re-edit your posts if you'd like, because I'd like you to find one more thing. So you can re-edit your posts and press submit once you change it. But here's one last thing. All right? Here's a point class. Let's say that we take our point class, right? Keep everything that we have already. Keep it all. And add this method called reset, right? That's meant to, like, for some reason, reset the points x and y to 0 to make it 0, 0, right? And here's the implementation of that reset method, right? There is something very, very subtly wrong with this implementation right here. It is not going to do the resetting properly. Do you see it? Try to find it. It's a very subtle issue, but it's a very insidious issue, right? It's really horrible, the problem here. It's going to mess everything up. It's not going to set the x and y properly. See if you can figure out why. All right? Think about how I did other things that set number variables. If there's something wrong, take a couple minutes to discuss. My hint is there's nothing wrong with the separation up here. It shouldn't be constant. That's fine. It's meant to change it. But it's not going to change it for some reason. All right. This is kind of one of those ones where either you see it or you don't see it. So it's okay if you don't. Did anybody find it, though? Ooh, nice, nice, nice. It looks like we did. Awesome, awesome, awesome. A few of us saw it, and I'm going to help you see it, too, if you don't. All right? Also, remember to do attendance, because I forgot to end that. I will end that within the next time I think about it. So you have at least a minute. All right? But good job. It looks like we're seeing it. So for those of us who didn't, it is very, very subtle. Why do I have that visible? Something is wrong here. There we go. All right. So let me implement this reset and we'll try it, right? Let's do like a reset test and everything. We'll figure it out. Where do I want to put it though? So let's implement it. Let's like add this declaration to the header file. Let's do that. And we'll say, let's put it down here. It's like, this is the one from the crash test. It's going to be void reset. Right, so just meant to be called on the line by itself. And so here is the implementation that we had. Oops. And there we go. Void reset. We got to say point : reset. And then the body looked like this. Let's see if this copies and pastes normally today. Of course not. All right. How do I want to fix this? So let's copy that. Replace that with a normal space everywhere, please. I don't understand why that never works. Okay, so there's the bad implementation. Keep that over here. Let's go to the main file. Let's add a test for reset. I guess I will call it test reset. That would make the most sense to me. Let me prove to you that there is an issue right now. Let me do, let's just copy this one maybe. We'll call it test reset, of course, though. So like it was, the x and y were these guys, maybe. And then we say q.reset. And then we should see that the x and y are zeroed out. That's the goal, right? 0.0, 0.0. Reset. All right? So there, let's see if I can keep that over there. It's as good as I can do. All right, so that's the relevant code, and I'm calling this in the main file. And we're going to run this test. Fails. All right, so there's something wrong. All right, if x and y aren't 0, well, we can print them out. Let's see what they really are. Cout q.getx, and just like a space between them maybe. Q.getY, and new line. Point. They are still set to 2.5 and 3.5. So these lines did nothing. You see a little more now? So look at this setter right here that's changing y. If you didn't see it before, do you see the difference now? This is not setting my y, but this one was. You all seen what's different about those lines? Double, right? The second you say double, what happens is it makes a brand new variable, right? The second you say the type name of something, that's creating a brand new local variable in this case, also called y. And that, of course, takes priority because it's closer. And it's a local variable. It shadows your member variable, also called x and y. See the problem there? That's the issue. And so these are just local variables. They're just for this reset method only, and they die once reset returns. And so it's setting something called x and something called y to 0, but it's not what we expect. All right, so here's what's going on, and I can helpfully show you the problem with the stack diagram. So here we were in main. And main called test reset, right? So here we are in main called test reset. So we're up here in test reset, and we made a point Q. Well, let's see, how do I want to do this? So yeah, here we had test reset. And then we made a point Q, and it held in its x and y 2.5 and 3.5, right? 2.5, 3.5. And then now we called q.reset. So we're going to jump up into the body of reset, right? Let me draw everything that reset knows about in green. So now we're in the body of reset. We're saying q.reset yourself. Remember that all of your member variables at the start, they are all visible. Like if you just said x, you would be getting q's x. If you just said y, you're getting q's y. But we did this. We said double x equals 0, double y equals 0. And what did that do? That made brand new, and those got priority, brand new local variable called x set to 0. Brand new local variable called y set to 0. Double still. And we just shadowed our member variables. Do you see that? That was the problem. Then once reset returns, of course, those x and y's go away. They're just local variables. They weren't actually our member variables. Okay? Does that make sense now, the problem? We're shadowing things. That's the technical term, I guess. So, yeah, let's fill this out so you can notice this later. You would be surprised as to how many CSCI 41 students still do this wrong. So I'm glad that you will never do any issues with it now. You'll remember this forever, right? The following code creates new local variables called x and y. They shadow the x and y member variables. Okay? Question? So if you wanted to reference the variables that we're defining in the class, would you do point.x or something like that? Or would it just be without redefining? Just like you were doing here. It already exists, just use its name. Yeah. So let's comment these out and let's do it right. Yeah. So it's just, it should have been just like my x member variable. It's already in existence. Call that 0, make it 0. Same with y. That's the right way. And so now I really will see 0, 0, and that will pass my test. Okay? I think that is the idea. Any questions about any of that? I think it's a very long example file for the day. Yeah. Nope, just like we already correctly set member variables in our setter, so it's the same pattern. Yeah. Yeah. Nice. These are good thoughts, you guys. All right, and so that is, I believe, where I want to stop for the lecture. There's still more to learn about classes. It's a lot. We'll get there next time. I promise to stop that. But yeah, before I let you just go off and work, I want to release 2 things. Let's do lab 5 first. Let's give you a new lab. Yeah, you'll have a couple weeks to do it. Definitely start early, though. There's a reason I'm giving you multiple weeks. So this one is on a concept called rational numbers. If you haven't heard of those, I promise you have. Just with a different name. Standard code 4005. There they are. So, all right. This is about your lab. So rational numbers are what this lab is on. It's a functions lab. So finally we're using functions, making our own. So first of all, we're going to make a library that works with these things called rational numbers, which is just a pretentious way to say fraction. Okay, that's the mathematical fancy form to say fraction. Okay, so every rational number looks like this. It's a ratio of 2 numbers. It's an a over a b, right? Where a and b are integers. That's what it means to be a fraction. That's a rational number. And so we're going to work with rational numbers and like add them together. You know, you have to like find a common denominator. So there's some cool programming stuff that we can do with these guys. All right. So multiplying 2 rational numbers, that one's easy because you don't have to find a common denominator. You just multiply numerators by denominators, right? Addition, though, is hard. So we'll save addition for a future lab on rational numbers. But something that we really like to do with fractions is to simplify them, right? So every time, here, let me make a new slide for this. Boop. This is about your lab. I hate that it does that. Your lab. Let's go back to blue. So you don't usually, you write 2 over 4, but you mean like you don't want it to stay 2 over 4, right? That's lazy. You want to simplify it to 1/2. Yeah, somehow. Yeah, we like to work with simplified forms of fractions. And so there's an algorithm for that. Let's talk about it, all right? So let's see, how do I want to do this? Yeah, so here are the files. I've given you these files. And yeah, let's just go through them, all right? So I've given you a header file. We're making a rational number library, all right? And the header file defines all the things that exist in that library. There's going to be 3 functions total, all right? And anybody who wants to use our functions can include our library. Boop, rationals.h. And so here are the 3 functions that you will make that work on rational numbers. There's the first one called rational pretty string. It takes a fraction as the 2 pieces, right? A numerator and a denominator. And we're going to give back a string. We're not going to print it out. We're going to make a string that makes it look pretty. We're going to simplify it, like put some spaces and some slashes and stuff, like get it ready to be printed, but don't actually print it. So convert it to a pretty string. Here is the multiplication. So rational times is going to take 2 fractions, numer 1 and denom 1, numer 2 and denom 2, 2 fractions. Excuse me. And it will return a 3rd fraction. One way to return multiple things is to use reference parameters. So here I need a result numerator and a result denominator. I'm going to pass those by reference so that I can fill in somebody else's memory. That's one way to return two things, two ints. Okay, so that's good. You'll multiply them and put the result there. And then simplification is the last one. Simplify a rational number into its lowest possible terms. And so we want to also pass a fraction by reference here. We want to be able to change the numerator and the denominator from 2/4 to 1/2. Okay, so that's the idea. I hope that makes a little bit of sense. So those are your three functions that you will be implementing. All right, and how do I want to do this? Yeah, and you'll be implementing them in the CPP file. So rationals.cpp is where you implement all the things in your library. All right, and I guess we should talk about simplify first. All right. Simplification of rational numbers has to do with, or you're going to end up using the greatest common divisor function, which I've already given to you. So you remember that we made this in class once upon a time. This will help you simplify your fractions, and I'll show you how in just a second. But this is also another case of information hiding. This is in the CPP file, so it's not actually part of the header file. It's not in the library. The user doesn't even get to know that we're using GCD. It's just for us, all right? That's perfect. It's just a helper function for us. So we're going to need it for simplification, and here's the secret. To simplify 2/4 to 1/2 in a program, what you can do is give to your greatest common divisor algorithm, GCD, just give the numerator and the denominator, and it will find the biggest thing that goes into both of them, the greatest common divisor. Yeah? What's the GCD of 2 and 4? It's 2. That's the biggest thing that divides into both of them. And do you see how if you divided the numerator and the denominator by 2, you would get 1/2? That will do your simplification for you. Okay, that's the secret. There is a little bit more to it. So you're getting these things by reference. So you're going to change numer and denom. But GCD only works with positive numbers. You can only give it positive. You can give it 0 as well. Only non-negative numbers. All right. So say you had this fraction, 4/-8. That is a problem. All right. GCD cannot accept -8. It will not work. So what you have to do is you're going to have to get rid of the negativity for a split second. All right, you're going to have to figure out, was your rational number negative or positive by checking 3 possible cases, right? If the numerator is negative and the denominator is not negative, it's a negative fraction. If the numerator is positive but the denominator is negative, like this example, it's still a negative fraction. If neither are true, then they're either both positive or they're both negative, and in either case, the negatives cancel each other out. There is a positive fraction at that point, okay? So you got to figure out if it's positive or negative and save that for later in like a bool, because you need to make those numerators and denominators for a split second positive so you can feed them into GCD. Does that make sense? You need to do that because GCD does not accept negative numbers. So you have to save for later, figure out if it's negative first, make all those things positive, numerator and denominator, make them positive so that we can use GCD, do the simplification, and then let's say that our standard form for negative fractions is we make the numerator negative. So we're going to like create positive 4 and positive 8 for a second, get rid of the negative. Remember that it needs to be negative though. That will compute 1/2, right? And then bring back in the negative into the numerator. That will be our standard form for simplified fractions, okay? Make sure the numerator is the negative thing if we decided that it was a negative fraction, okay? So that's that. And that's it. That is your implementation. After you do that, by messing with these variables, you've essentially simplified that fraction because it was somebody else's variables, right? Because it was passed by reference. Yeah. No, yeah, the way I want you to do it in this library is to do it in the numerator because most people don't write their fractions like that. That's abnormal. So this is the standard way people write negative fractions with the numerator negative. Yeah. That's just the way I want you to do it. All right, so that's that one. That simplification, you're going to use that in every other one. All right, so for rational times, it's very easy to multiply 2 rational numbers, right? You're given numer 1, denom 1, like a/b, and c/d, numer 2 and denom 2. And to multiply them, what is the answer? It's ac/bd, right? Very simple. So you'll compute that. You'll shove the answer into result numer and result denom. That's like where your fraction result should go. They're reference parameters. And I want you to get a simplified final answer, though. Make sure to call simplify on your result to make sure that whatever big answer you got back gets shrunken down to the smallest terms that it could be in. Okay? Make it all nice and pretty, especially because these could have been like negative as well, right? So you also want to make it pretty, make sure the numerator is negative, and simplify takes care of all of that for you, right? You already did that. So that's multiplying fractions. Does that make sense? Rational times. Multiply two fractions together, simplify the answer, shove the final result into result numerator and result denom. That's that one. And then finally, rational pretty string. All right. Right now it's just a stub. You'll have to fix it. But what I want you to do is return a very pretty version of your rational number as a string. All right. So for example, if your numerator was 2 and your denominator was negative 44, so the simplified version of that is negative 1 over 22, right? You got to simplify it and then also make it pretty. So the final string that I want you to return, if that was your original fraction, is negative 1 space slash space 22. All right? So include some spaces and a slash. Make it pretty, ready to be printed. But don't actually print it. You're just returning a string. Okay? And like if numerator was 2 and denom was 4, your final string that you give back should be 1 space slash space 2. That's our pretty version of that fraction as a string. Does that make sense? That's what you're going to be doing. And so you need a way to get a string out of a number, don't you? Like the reverse of what we kind of did before for like command line arguments. Like we needed numbers out of strings. Now you want to go the other way. So your string library has a very handy toString function that you should look into. All right? Because you can say toString on any number, on like 42, and it will give you back the string 42. And then you can start, like, you can add a space, add a slash. You can do the string arithmetic with the plus operation. Yeah? So that's my hint for you for rational pretty string. Use toString to make, after you simplify these things nice and small, and then build up your string with that in mind. Okay? Any questions about pretty string? You're not printing, you're just returning a string. Somebody else will print. Or check your answer. Right? So that's that. What else do I want to do? Is there a question in the back? No? Alright, let's see here. So, yeah, that's that. Make sure to give back that string. Don't print anything out. Yeah, rational simplify and rational times are doing call by reference things, so they're changing stuff. And yeah, I've given you 2 files with main functions in them that both use your library. So you have 2 separate files that you could compile, right? I've given you sampleprogram.cpp. That's just a simple program. So it's called sampleprogram.cpp. That kind of uses some of your functions, like enter in the first one, enter in the second one. So it allows you to enter in a fraction to test your own stuff. And here it's calling rational simplify. It's printing the pretty version of it, etc., etc. Doing the multiplication, printing the pretty version of that. So it's just call on your stuff so you can check it, make sure it's working. So like here's an example run of the sample program. And to compile, you have to give your library, remember, to G++. So like you could say 2 over negative 22, 4 over 8, and like it'll simplify them, like simplify the first one. It'll pretty print the second one, which should also simplify it as it's printing it. And then like it's going to do the multiplication and make sure that the answer looks nice and simplified too, right? So like it's just checking that everything works. So you should see that for that example, but try it yourself. And that's one way to check your answer. So that's your first bit, but that's just helpful for you, right? I've given you another file with a main function in it, and that is what you're going to be tested on. I'm giving you a bunch of tests now too, all right? So here's some tests with assert true now, okay? So it's test in our library. I've made a few of them. So test for simplify. Test for simplify, making sure like this should have happened to those variables. They should have changed those values into that form. Test for multiplication with assert true. Test for pretty string with assert true. So make sure those pass. That's going to be my test file, all right? So that's, you compile it like this. You still give your library. It's still using your library, but it's a new main function file. Test.cpp. Sample program, okay? So that's that one. You should see my tests pass, and then you can be even more confident that your library is working. This is why it's a 2-week lab. There's a lot to explain. So there's that, and then once those tests pass, I want you to write tests. It's your turn, all right? So after you get these to pass, I'd like for you to, in the same style, come up with some wild scenarios of maybe combinations of these functions or something, I'd like you to write 2 more tests. So use my style, like make a function for each of them, call assert true exactly once, but maybe you can like test multiplication by 3 fractions, like keep on multiplying fractions into a 3rd fraction or something, I don't know. But like come up with some scenarios and call assert true to check something. You can test whatever you want, as long as you're using your functions that you made, okay? So I want to see, that means I want to see passed 5 times in your final output, all right? Because I got my 3 tests, and then you're adding 2 more. Does that make sense? So you're going to use assert true, come up with your own random scenarios. It can be as complicated as you like, but that is your last assignment, last part of your assignment, okay? You're going to write your own test, 2 more tests to make sure everything is nice, and then you're good to go. So this sample program is just for you to help as you're getting ready to use the actual testing file, okay? So yeah, that's it. The only files that you will be turning in will be your implementation of the library, so you're not allowed to change the header file. The autograder is going to use the default original header file. You can't just like go implementing stuff in there or anything, you can't add anything. You have to use the original header file, because that's what you're going to be tested with. And you get to modify rationals.cpp, so you're turning that in, and then you're adding some tests to test.cpp, so you're turning that in too, right? So that, I think, is everything that I wanted to say about your Lab 5. We good? Yeah. Yes, that's exactly. You can change, though, I've given you this sample program. You can change sample program too, because you're not turning it in. And that's not changing anything. But yeah, the header file for the rationals library you cannot mess with. Yeah. All right, so there's all those. And yeah, I think that's everything I want to say about your lab. There's one last thing I want to talk about, though. So I want to release what's called the mid-semester anonymous feedback survey. So we are in week 8. There are 17 weeks of classes plus a finals week. So integer division, we're in the middle, right? So I like to give out just every semester for all of my classes just a little anonymous survey. It's a Google form. You can click on it, and you can fill it out and give me feedback about how the class is going for you. I cannot see your name. Your name is completely anonymous, right? It's not tied to you at all, so you can be as mean as you want. But I think it would be helpful to get your feedback, especially if there's something going horribly wrong in the class. Like, there's time to fix it while you're still a student, right? And then obviously, like, your feedback will help me for all my future students. So, like, I'd appreciate your feedback if you're feeling like giving me some. But here's some of the questions that you can answer in as much or as little detail as you would like. Give me 3 things I should keep doing, stop doing, start doing, stuff like that. Stuff that would help me and you and my future students. So I would appreciate your feedback if you would like. Obviously, I can't tell if you did it or not. So you don't have to do it, but do it if you would like. And that is your mid-semester anonymous feedback page. I think that's everything that I wanted to say. Are there any last questions about anything? Yep. That's when I'm going to look at the answers. Yeah, I think so. I mean, there's no actual due date because it's not for a grade. That's when I'll not look at it again, I think. Yeah. All right, so if we're good, that's everything I wanted to record for the day.